Okay. The last class we proved something called weak law of large numbers. So I mean, the law says something about some sort of convergence. So I will define some convergence of random variables. There are different modes of convergence for random variables. So we'll define two of them, and we will prove the law of large number in terms of those convergences. So if you have a random variables, if you have to define random variables, you should always have probability space that will be behind. I mean, that will be in the background. Okay? So you have a probability space. Okay? And so you have a sequence of random variables. And it need not be, we have been working with discrete random variables. It need not be discrete. This holds generally. We haven't defined what a random variable in general, but when we do that, the same definition will be used there. Xn is countable. What is countable? Discrete random variable is range is countable. Yeah. Okay, this is the random variables, real valued random variables. Then first definition is we say Xn converges to X almost surely or almost everywhere, whatever, almost surely. When it is probability, we say almost surely. When it is just a measured space, we say almost everywhere. So if the probability of wherever it doesn't converge is 0, or the probability with respect to the P of X over all those omega such that Xn omega converges to X of omega equal to 1. Okay. So outside a set of measure 0, it converges pointwise. That's what it means. Okay. Xn converges to X pointwise. I mean, there is something called uniform convergence and other things. So like the pointwise convergence means at each point it converges. Xn of omega converges to xy, x omega in each point. And it happens on a set of measure 1. Outside a measure 0, so this is one thing. Then we say, the next definition is we say Xn converges to X in probability. Yeah. All probable events, where is the event here? Outside an improbable event, I mean, that's what is clearly written, almost surely. That's what it means. Okay. It's actually surely, the language is almost surely. Okay. It converges surely, that's what it means. We say something converges, so the notation is this: Xn converges to X in probability. The P is that. Xn converges to X in probability. Okay. Probability, that's what I have written there. Probability. I'm writing it. Okay. We say, this is definition. We say Xn converges to X in probability. We denote it like this: Xn converges to X. This is a notation for that. If the set P of mod Xn, so all those omega, I mean, here you don't need to invoke see, here we need the probability space because you have a set of measure 0. Outside that, the convergence happens. Convergence happens pointwise. But here you only need the probability, which you can talk in terms of density function. You don't really need the probability space. Okay? Without that, you can do that, work with this. Okay. So the probability of this set, Xn minus X, greater than or equal to epsilon. Okay. This goes to 0. This is a number, a positive number. It goes to 0 for all epsilon greater than. So you fix an epsilon, arbitrary epsilon, you fix it, and then for that this goes to 0. Okay. First, we want to check that these two are legitimate notions of convergence. So for that, I mean, for a sequence, okay, if you haven't studied topology, then there is something called net, that the limit may not be unique, and there are situations where the limit may not be unique. But in general, limit will be unique. So first we will make sure that the limit is unique. Okay? So this is a small remark. It is easy to verify. Suppose if Xn converges to X almost surely, and also Xn converges to Y almost surely, we want to verify that X equal to Y. X equal to Y will not happen. X will be equal to Y almost surely. Again, outside a set of probability measure, I mean probability 0, they will be equal. That's what it means. Okay. So this implies xn. So this implies xn converges to x almost surely means this means there exists a set A such that P of A equals 0 and xn omega converges to x of omega for all omega in A complement. That's what it means. Okay. Similarly, xn converges to y almost surely means there exists a B such that probability of B equals 0 and for all omega in B complement xn of omega should converge to uh, xn of convergence, converges to x of omega. Xn of convergence should be to omega to y of omega, right? Almost surely, yes. Okay, I have written there, I think. Probability of A equals 0, yeah. Outside probability A complement, it goes. Similarly, B complement for all omega in B complement. Hmm? A is a null set. Could be. There's no could be. It is null set. P of A equals 0. P of B equals 0. Now you take another C equal to A union B. Of course, P of C is less than or equal to, of course, P of A plus P of B equals 0. So P of C is also 0. And on C complement, which is equal to, of course, A complement intersection B complement, x omega, x and omega converges to x of omega and also y of omega. So, but in real number, limit should be unique. This implies on on C complement, x of omega equal to y of omega. Okay. So, the probability of this set x equal to y is equal to 1. Okay. So, the limit is unique in this sense. Okay. Xn converges to x, xn converges to y, then x equal to y with probability 1. So, almost sure convergence is a genuine convergence. Okay. Okay. So, second, we can verify the same thing for the convergence in probability also. So, this is easy. I think this is clear. Okay. So, suppose xn converges to x in probability and also xn converges to y in probability. Okay. Then we want to show that again probability of x minus y greater than or equal to epsilon. We want to show that this is 0 for all epsilon. Okay. We take and fix an epsilon. I mean, let epsilon greater than 0, arbitrary epsilon greater than 0. We fix it for this calculation. Okay. It's arbitrary. X minus y greater than or equal to epsilon. Now notice that x minus y greater than or equal to epsilon will imply x minus xn plus y minus yn. Sorry, x minus yn. Okay. Maybe I should use omega. There I don't need omega, but here I have to need omega. X of omega minus y of omega for any omega is less than or equal to x of omega minus xn of omega plus x of omega minus y of omega. Okay. Now this is so this is greater than epsilon. So this is greater than epsilon. So this should also be greater than epsilon. Okay. So this set all omega which satisfies this will satisfy this, right? So this set is contained. So this implies x minus omega greater than or equal to epsilon. This set is contained in this set x minus xn plus y minus xn minus y greater than or equal to epsilon. It contains in this set. Okay. But then if this is satisfied, okay, then that will imply one of them should be greater than epsilon by 2. Right? So if this is satisfied, this implies x minus xn, x of omega minus x of xn of omega is greater than or equal to epsilon by 2. Similarly, x of omega minus, or one of them should be true. Okay? X of omega minus xn of omega, y of omega is greater than or equal to epsilon by 2. One of them should be true. So if you take the union of these two sets, that should be contained in this. So what I'm saying is this is less than or equal to, I'm skipping 2 steps. I hope you are well used to this. So this is less than or equal to P of x minus xn greater than or equal to epsilon by 2 plus p of x minus yn. Okay, this is greater than or equal to epsilon. Both will go to 0. Okay. I'm writing here. I'm other part I'm right just to. So this implies both will go to 0. This implies probability of x minus y greater than or epsilon is equal to 0 for all epsilon. Okay. So this implies, on the other hand, probability of x minus y greater than 0 is equal to probability of union of n equal to 1 to infinity x minus y greater than or equal to 1 by n. Okay. So that is, you take the summation of all those zeros, so it is 0. Okay. So probability of x minus y greater than epsilon is 0. So probability of x minus y equal to 0 is 1. Okay. Is 1. This implies x equal to y almost surely. Okay. So convergence in probability also, the limit is unique. Unique means x is equal to y almost surely. Yeah, yeah. Where? Yeah, one by one I will go. One by one I will go. So this proof is clear. Almost sure proof is clear. There is nothing. You take two sets, measure 0, you take the union and finish the job. Okay. Here what happens is, I want to show that this set, this has probability 0. Okay. So this set is contained in these two relations. This relation will imply this relation for each omega. So this set is contained in this set. So they should have smaller probability than this. So that's clear. Then if this is greater than, this is clear. I proved for this, but this is also clear. What is not clear to you? After this, okay. This is this greater than this is, so this can be written as union of this. So I am taking the sum. It's all less than or equal to sign. It goes through. This goes to 0. This goes to 0. There is no n here. Okay, so this goes to 0. This should be equal to 0, right? This is less than or equal to this. You take the limit. There is no n here, right? So there is no limit here. This is just something constant in n. So here it depends on n, which goes to 0. So this has to be equal to 0, right? This is less than or equal to all of them. So this is equal to 0 for all epsilon. So that is, if you take the union over all those sets, for take epsilon equal to 1 by n, union of all those sets is exactly greater than or equal to 0. P of that is 0. So P of x minus y equal to 0. The modulus of x minus y equal to 0 is 1. So x should be equal to y with probability 1. That's all. Okay.
When does one convergence apply here?
Oh, I didn't move it here at all. Okay. When does almost sure convergence will imply probability convergence. Probability will not imply almost. We will see this again later. We will go through all this after proving continuous variable. After discussing continuous variable, you will go through. We will introduce one more convergence in mean. So maybe one or convergence in moment, kth moment or something. All those things we will introduce, and after that we will go through. Unfortunately, the camera was pointing in that, but it's okay. Okay. So the last class, what we proved is the following, which was proved in the last class. If xn is a collection, we have a countably infinite collection of independent random variables, which we call it as IID. That means independent and identically distributed, IID. Okay, independent and same distribution. Okay. They all have the same distribution. So independent and identically distributed. Okay, then and with E of, one of them is enough. E of x1 is less than infinity, and E of mod x1 square is also less than infinity. We assume this. This is not actually needed, but with this, the proof is easy, as we have proved. Okay. Without that, the proof is more difficult, which we may prove later when if we have time. Okay. But we have proved this. The proof is very easy. Then, if you take Sn equal to summation xi 1 to n, then Sn by n converges to E of x1. I mean, sorry, E of x1 equal to mu, then it converges to mu in probability. This is what we prove. I mean, how did we prove? We just have to talk about this probability of Sn by n minus mu greater than or equal to epsilon. We want this to go to 0, but we proved this probability of any x greater than or equal to c is less than or equal to E of mod x power k divided by c power k. We proved this inequality. Okay, using that, but here the variance will come. I mean, if you can take the n above and the Sn will have this is less than or equal to sigma square. If you take the variance sigma, I mean, it will be like variance of Sn by n times epsilon square. But variance of Sn by n is 1 by n 1 by n times variance of Sn 1 by, I mean, you can take the constant house as n square, and variance of Sn is n times variance of x1. Okay, so n times variance of x1 divided by epsilon square. Okay. That's the law. If you take, instead of you take 2 k equal to 2, you get this. Instead of x, you take x minus mu. Sorry, any x minus mu. Okay. We did all this last year. Okay. So this is equal to variance I divided at sigma square or something, n epsilon square, this will go to 0. Okay. This goes to 0. So we proved it in the last class. This is what is called weak law of large number. Okay. Okay. Now we want to prove a stronger version of this. Okay. That's what we want to prove under some more condition. Okay. Here we assume only two conditions. The expectation exists and the second moment exists, which is same as variance exists. Okay. Okay. So this we go a little bit slowly. This is strong law of large numbers. Okay. Okay. So again, the same assumption, xn. It's a sequence of IID random variables. Sequence of identically distributed independent random variables, IID random variables. Okay. Xn. Okay. So such that we assume the following: E of x1 power 4 is less than infinity. I mean, if x1 power 4 is less than infinity, x1 cube, x2, x square, everything is less than that. Okay. And ex1 equal to again mu. Okay. Then, I mean, and Sn, select Sn equal to summation xi divided by n. Then Sn by n converges almost surely to mu. Mu is a constant random variable. Okay, it's a number. It's a constant. I need it here. Before this, you asked it once earlier, such that, so that. Okay. You're again shocked by this notation. I mean, you can write ST also, such that. This is something very common notation. This is used. Okay. Okay. So it's the same statement, except that it converges in almost surely, and we assume something more. The fourth moment exists. Okay. And well, we need it in the calculation, but it's not actually needed. You can prove it only with this assumption. The first moment exists only with the expectation less than infinity. That is enough. Okay, but then the proof is more difficult and it will take some time. So if we have time, we will prove it later, but this is for the time being. Huh? Huh? One by one. No, it's whole thing divided by n. Yeah. So, sorry, Sn there is no division. Sorry. No, there is no division. Yeah. Sn by n. I'm putting it here. No, so yeah.
Oh, sir. So that was the only
There also, one second, there also I have written like that. That's correct. You tell me, yeah. It's almost sure convergence. Yeah. Almost sure convergence, and it refers to the probability space. There is no need for reference to probability space. It's only the probability which matters, which you can calculate using density function or something. You can just talk about random variable without referring to the probability space. But here you need the reference to probability space. Of course, because you are saying of each omega, this, what does this mean? There exists a set A contained in omega. See, you have to include omega such that probability of A equals 0. And for all omega in A complement, this Sn omega divided by n will converge to mu for all omega in this. Yeah, this is a strong condition, stronger condition. You can remove it, but I mean, the proof is long. Okay? It's difficult.
this theorem proof.
Without any condition, only this expectation exists. With that, it's true. It's true. Okay. So before the proof, I want to recall a few things which you have already done in quiz and assignment, so which I want to recall. So this is just a recall. If you have a collection of set an, then you can talk about this. M equal to infinity. This is decreasing. This is decreasing sequence in n. Then you take the intersection in n equal to 1. You know this. You already know. Okay, and this limit. I mean, this is the probability of this this set. I mean, this is some sort of lim sup kind of thing. This is equal to, I call it as lim sup. I mean, I don't need what you have done in the assignment. I don't need the whole statement. You can define lim means by interchanging intersection and union. This is lim sup of an, lim sup of some set. Okay, this is an I mean, when you fix n for each n, this is from m equal to n to infinity. So if you call that as bn, then that bn's are decreasing. You take the intersection. Okay, that is the limit of the set. This is what is called lim sup. Very similar to how we define for real numbers. Okay, you take the supremum and that will be a decreasing sequence. So you take the infimum. Okay? So it's very similar to that. Okay. So then we know that this lim sup of an, which is a set now, this is contained in each of this m equal to n to infinity am. Okay. So probability of this is less than or equal to probability of for all n. Okay. This is true, right? Okay. So if this goes to 0, this should be equal to 0. There is no n here. I mean, you have taken lim sup. There is no n here. This is just a fixed one. Okay, a constant set. Okay, it's not a function of n. Okay, so if summation n equal to 1 to infinity p of an is less than infinity, okay, then which is equivalent to saying, I mean, by definition, this means summation n equal to m equal to n to infinity p of am. This goes to 0 as n goes to infinity. That's what the definition of this. Okay, that's the definition of convergence of a series. Okay, that is equal to 0. So then if this is true, then that implies p of lim sup of an equals 0. Okay. If you have a sequence of set such that summation of Pn is summable, positive, so it's just summable, there is no confusion about it. P of An is less than infinity, so it is convergent. It's an absolute convergent sequence. then probability of the lim sup of an equal to 0. This is what is called Borel-Cantelli lemma, I think. Borel-Cantelli lemma. Okay, we will use this to prove this. We will use this. This here to here. These two. That is the definition. I just put equivalent to. What is the notion of some convergence? Sn summation n equal to 1 to n some number xn. A sequence xn converges if sum up to k equal to 1 to n converges. That means precisely the tail terms goes to 0, right? Here we write it because it's absolute. There is no. See, usually it just means Sn converges as a sequence. But here you can actually make the tail things sum. You can sum, the sum may be infinite. Okay. But the tail thing you take that goes should go to 0. That is a definition. Okay. Okay. So we want to use this. So for that we want to define some set. So this is the proof of strong law of large number. Okay. So okay. So what does it mean? We want to prove the following. Want to prove probability of this set where Sn, okay, without loss of generality. First we assume that otherwise this we have to take care of mu. Okay, without loss of generality, I write without loss of generality, assume mu equals 0. Okay, if you want, you replace x minus mu. Okay, you can replace x by x minus mu, and we can, I mean, the whole thing, and you can assume that, I mean, that will become, if you want, n mu or something. So this is okay. Okay, so you can assume mu equal to 0. Okay, so we want to prove probability of this set Sn by n goes to 0, okay, equal to 1. That's what we want to prove. That is, we want to prove probability of Sn by n does not go to 0 equals 0. That's what we want to prove. Of course. Okay. So what does it mean by Sn by n does not go to 0? What does it mean? Okay, come on, tell me. Given convergence means given epsilon, there exists. Convergence means given epsilon, there exists a capital N such that after that capital N, everything is here at 0, the limit is 0, so less than epsilon. There exists, let us call it epsilon naught because we are fixed for all.
There exists somewhere.
So, no, there exists, no, for all N, you are right. For all capital N, there exists a N greater than or equal to N such that mod of that whatever is less than greater than or equal to epsilon naught. Okay. So let me write it again. So there exists, so this means Sn by n does not converge to 0 means for all k there exists a nk, okay, whatever that is nk increasing. Okay, I mean k is greater than k, so you can assume that you can take it to be increasing if you want. Nk greater than nk such that Snk by n is greater than epsilon naught. Okay, there exists epsilon naught greater than 0 such that this is okay. You agree with me? There exists epsilon naught such that this is greater than 0, greater than epsilon naught. There exists epsilon naught such that for all k, I mean there is no all k. There exists a nk. There exists, I mean for all, I wrote the definition for all nk, but instead I take nk k equal to 1 to infinity. Nk goes to infinity. I take a subsequence. That's all. I have a subsequence such that this happens, or Snk by n is greater than or equal to epsilon naught infinitely often. You understand what it means? Infinitely often. There are infinitely many nk such that are snk for infinitely often. I mean, right? That is, if you take, let an equal to Sn by n greater than or equal to epsilon naught. Okay. Then omega is in lim sup of an. That means what? Omega is in, I mean, this is equal to intersection union, n equal to 1 to infinity, m equal to n to infinity, an, right? This means omega is in union of m equal to n to infinity, am. Okay, am. Okay. This implies omega is in am for some, I mean, this n may depend on that, m for some m n greater than or equal to n. So this just means that omega is in am infinitely often. Correct? I think my handwriting is better now. Okay. I'm saying that you take this set to be this. Okay. Then omega, suppose omega is in this. Okay, that is equivalent to saying this. That is equivalent to saying this. I mean, these are all both ways true. So infinitely often. Okay, that's what it means. Okay, if you take that to be epsilon naught. So to prove this theorem, it is enough to prove the following. So to prove theorem, it is enough to prove, okay, probability of lim to, I mean, for all epsilon greater than 0. So I want to call it as a epsilon, a n epsilon, right? I mean, fix epsilon, okay, fix arbitrary epsilon, arbitrary. Okay. Instead of epsilon naught, let me have epsilon. Okay, whatever. Let me call it as an equal to all those Sn by n is greater than epsilon. Okay? Greater than or equal to epsilon. Okay, it's enough to prove lim sup of an. This probability of this. Probability of this equals 0. It's enough to prove this. Is okay? Shall I go through again? Yeah, let's. No. We want to prove P of this equal to 0, right? So we want to consider this set where this does not happen. So we want to prove the probability of that set is 0. Okay? Wherever it does not converge, that means there exists epsilon naught such that something happens. So there exists epsilon naught such that that difference is greater than epsilon naught for arbitrarily, I mean, for infinitely often, for infinitely many. It need not be after some time or something. I mean, see, that is, which is equivalent to saying omega is in this. See, if you have a sequence of set an, okay, lim sup of an is a set where omega is in an infinitely often. That's what it means, because omega is here means it is in all of this intersection of all of this. It's intersection. I mean, it is in this intersection means it's in all of this set. That means it is all of this m equal to 1 to infinity. Means it should be one of them. After this n, it should be in one of them. That is equivalent to saying it is infinitely often. Okay? Omega is in am infinitely often. Okay? If anybody has a problem with this, so that is what infinitely often. So here also it is basically infinitely often. So if I take this set for each epsilon, for any epsilon, I take this set. Okay. So I am just taking this set an equal to this set, not just, I mean, that does not exist any epsilon naught. That's what I want to say, right? That's what I want to say. So I have to take for all epsilon, I have to prove this. There exists an epsilon naught, it says. There cannot exist any epsilon naught. That's what I want to say. So I want to prove it for all epsilon. Okay. So an equal to Sn by n greater than or equal to epsilon. Now I take this. So with that discussion, what we have done, it is enough to prove that probability of the lim sup of an equals 0. Okay. Which is enough to prove summation P of an by the Borel-Cantelli lemma, which we have proved equal to 0, which is enough to prove this. So we have to get some 1 by n square somewhere that should be summable. Okay, that's what we want to prove. Okay, Now we want to consider this. So we want to consider this set. Probability of this an is this. Sn mod Sn is greater than n times epsilon, okay, which is this set, same as this set. Okay. Now we want to prove that we want to compute this probability and get a bound by 1 by n square or something, then it will be summable, right? That's what we want to do. Okay. Now we use the Markov inequality that will be less than or equal to expectation of mod Sn power. There is no power 4, so you can take the mod. Yes, these are all. Yeah, you said something.
You said we wanted a square.
When this has a n, no, this is less than or equal to some constant times 1 by n square. Then we will get the theorem, right? Because 1 by n square is summable, which is, sorry, this is finite. Sorry, finite. That's finite. Yeah, you are right. Sorry. Yeah. But I mean, we want to use the Borel. It's finite. Okay. Yeah. So we want to get this is less than something times 1 by n square. So which is summable, right? That's what we want to prove. Okay. Summation Sn greater than or equal to n epsilon. There is no need for mod here because this is all positive and we are not working with complex number. We are working with real number, so it's fine. Okay. Okay. Now we want to compute E of Sn4, Sn power 4. Okay. Sn power 4 equal to x1 plus up to xn power 4, right? Huh? What? This? No. I didn't write it fully. I want to Sn power 4 divided by n square epsilon 4. N power 4, sorry, n power 4 epsilon 4. This is the inequality we use. Chebyshev inequality, Markov inequality, whatever. Sorry, forgot. Yeah. Okay, that's okay. N power 4, epsilon power 4. So we have n here. So we have to get it somehow by n square. Then that n square will cancel with this and we'll get an n square, right? That's what. So E Sn power 4 we want to somehow compute. Okay. So Sn power 4 is this, of course. Okay. Now this is equal to summation xi power 4 I equal to 1 to n. Okay. Plus summation, we will get terms like this. Okay. Xi cube xj I not equal to j. Okay. Where it varies from 1 to n. Okay. Plus summation x I square xj square. Okay. Plus summation xi square xj xk. Okay. Where I not equal to j, I not equal to j. I mean, they are all not different. All three are different. I, j, k different. Okay. If it is same, it will be one among them. Plus summation xi, xj, xk, xl. Okay. Where it's all different. Okay. Different. That is how the summation will look like. Okay. Okay. This is the sum we have got. I want to show that only this term and this term, when you take expectation, that will remain. Other thing will have expectation 0 because we have assumed the expectation to be 0. So what are all the terms we have? E of x cube, E of xi cube, xj is equal to E of xi cube. It's independent, no? Xi cube, E of xj. Okay. Now this is equal to 0. Okay. Similarly, E of xi square, xi, xj, xk equal to E of xi square. I mean, independence means even if you have a function of that, it will factorize. Okay. E of xk, which is equal to 0. Okay. Similarly, how many more terms are there? Huh? We assume it without loss of generality. You replace x by x minus mu. This is just for our simplicity, or you have to compute those mu's and do all this calculation, okay, all these things. So you prove the theorem just to make life simpler. Okay, you can do with that also. You have to take care of that everywhere, and that's all. Okay, that is because of that. So similarly, E of xi xj, xk, xl is also equal to 0. Okay. What is the problem? No problem. Okay. Yeah, that's all. Everything. So only terms remains is the following. So E of Sn power 4 equal to E of summation E equal to 1 to n E of xi power 4 plus summation I not equal to j E of xi square xj square. Only these terms remain. Okay, but they all have the same expectation. They have the same distribution. So this is just n times E of xi power 4 plus this is only how to count how many of them. They all have this. So this is equal to summation. I mean, this is equal to E of xi square times E of xj square. Okay, which is just sigma square. I mean, mean is 0, which is just the sigma square of that. Okay, so this will be sigma power 4. You just have to count how many times it comes, how many times it will come. So this is just choosing ij from n, so which is n into n minus 1 by 2. And then we have to fix this comes because there are 4 places. No, in 4 places you have to fix the ij, right? This xi square, xj square, how does it come? That is because you have 4 places where you have xi, 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 and the remaining places xj, xj. So 4 places you have to choose I in 2 places, then the other 2 places will be by j. So that will be 4c2, which is 4 into 3 divided by 2, which is 6. So 6 into n minus 1 by 2, you can do all the calculations. So this is just 3 into n minus 1 times sigma power. Exactly. So you don't really care. You just have to worry about the n, not, I mean, you have to worry about n. The 6 or 4 doesn't matter. You can put a constant. So you have a, so this is equal to n into e xi power 4. You have to careful with the n. Okay, minus 3 sigma power 4 plus 3 n square sigma power 4. Okay. Okay. So, so this is all this thing are after some time. I mean, this is less than or equal to, this is for all n. Okay, this is for n. This is c times sigma power 4. You don't need sigma. 3 times c times n, 3 times n square. This term will be less than n after some time. This is a constant term, right? Ex power xi power 4 is a constant number, does not depend on n. This is also a number which does not depend on n. Okay, this will be less than n something, right? Some n. So after some time, this is less than or equal to constant times n square for all n greater than n naught, for some n naught. Okay. For some n naught, this will also be less than some fixed constant times n square. The constant should be fixed, right? We are done. If you have any problem with that, you tell me. Otherwise, we are just done. We have just proved that what way we got. Yeah. So E of Sn power 4. So we have probability of what happens? Sn by n, right? Mod Sn by n greater than or equal to epsilon is less than or equal to E of Sn power 4 by n power 4 epsilon power 4 is less than or equal to some c times n square epsilon power 4. Okay. Now summation of this. So summation of this. Okay, let's write summation of P of Sn by n greater than or equal to epsilon is less than or equal to summation c by n square epsilon power 4 is less. That's what you want to prove. So this implies the lim sup is. So the almost sure convergence. This is using Borel-Cantelli lemma. We prove. Summed over n. For each n, you have this set. We want to prove the lim sup of that set is 0. So we prove the sum is less than infinity. We are using Borel-Cantelli lemma, right? over summation. This is our an. So p of an. This is summed over n. For each n, this is, that's why we got this 1 by n square here. Some constant times n square epsilon power 4, and we got this. Okay. I hope it's clear. Everything is clear. So this is strong law of large number. So this says that this happens almost surely. This happens outside a probability set of measure 0. It cannot happen, for example, you take just simplest one. Okay, of course, finite set, there is nothing like that. Nothing about, I mean, everything will have every point. Usually in finite probability space, every point will have a mass. So suppose if we have this set, head and tail, or 0, 1, or whatever, and you take infinite product, you do toss coin infinitely many times. Okay, so then the probability space is this infinitely many times. You cannot toss, but you assume that you are continuously tossing. Okay, so the power will come, no? Huh? Yeah. Forgot to move. So suppose if you take this, for example, okay, what this says is Sn omega by n will converge to mu almost surely, right? That's what this says. Okay, for each omega, it converges. It can happen only for a probability of, I mean, probability 1, for a set of probability 1. Okay, it cannot happen all the points. For example, if you take this set, okay, or you can take other examples also. In this is a point, no? H. You assume that H. Everywhere H. This will have probability 0. I mean, if you can actually compute. This will be actually equal to, it's uncountable. The set is uncountable actually. If you, what? No, everything is half. Every single point. The probability is 0, correct. Yeah, probability is correct. Yeah. Now I'm considering this random variable. You take this as omega. Okay. Then Sn at this omega, you take the random variable to be xi from this. I mean, this is our omega. Okay. Omega to r. Xi of any omega, bits, omega 1, whatever. Like this is just omega I. The ith coordinate you just take. This is just, you have the product space, and the random variable is just the ith coordinate. What happens? They will be independent by our definition and all that. Okay, they will be independent. So now you consider this xi at this, you take this omega, particular omega. Xi of omega is just sketched, right, for all of them. Okay. Now if you consider Sn omega, or you take, I mean, sorry, it should be 1. 0, 1 power. Yeah, it's power omega. Sorry. So now you take this 1, 1, 1, 1. Now this is okay. A random variable has to be 0, 1. It should take the value 0. So let it be like this. Okay, now it makes sense. This is equal to 1. Okay. Xi omega equal to 1 for when you take this omega. Okay. Now Sn omega is going to be the sum of that. That will be 1 plus 1 up to 1 by n, which is just equal to 1, right? Which is 1. So this will converge to 1. Sn omega by n. Sn omega by n will converge to 1, not to half. Half is the mean. Mean of this random variable is half. This is Bernoulli random variable. Its mean is half. Bernoulli random variable with each half. Okay, it takes the value 0 with half. This will half. So this has the, it's an infinite product of, if you don't know infinite, it's okay. You can imagine. I am trying to give a counter example where the conversion does not happen everywhere. It happens only almost surely. Our theorem says that Sn by n, Sn omega by n converges to mu for all omega outside a set A complement such that P of A equals 0. Okay. I am saying the convergence will not happen at every point. It is only almost sure, it's not everywhere. That's what I want to say. Okay. You just throw out a set of measure 0. Okay. You can't remove that set also. That set has to be there. That has some meaning. Okay. So yeah, but you can't every finite omega. Yeah, but then I mean, if you group it together uncountably many, then that's not 0. But where is countable? There's no countable point. The only sequence is countable. I'm saying that convergence will not happen at all points. So this says that Sn omega by n goes to mu for all for omega outside a set. This will not happen for all omega. That's what I'm saying. For example, you take this point. This is a in this infinite product. You take this point. Okay. In this xn is just the coordinate. What is the value in the coordinate xn omega? Then Sn omega will be 1 plus 1 up to n. That will be the n. N by n is 1. So this Sn omega will converge to 1 for this omega. Most of the omega, it will not happen, right? If you take it, I mean, but on a probability, a set of probability 1, it will happen.
So can you the same measure here?
Measure? Every single point has measured probability 1, probability 0, I say. Now, what is there to relate? Here I said, you have a set A whose probability is 0. Outside that set A complement, this convergence happens. That's all. This is how we defined almost sure convergence. And we proved this law of large number where that this convergence happened almost surely. Okay, that's what we defined almost surely like this. Then we proved that this convergence happens almost surely. That is law of large number. I am saying that you can only ensure the law of large number only ensures that the convergence happen almost surely, not everywhere. It will not happen. Here is a counterexample. You take this 0, 1 set, 0, 1 product. You take 1 everywhere, for example. Okay. Then Sn omega by n will be 1 for all n. So it will converge to 1. Okay. So it will not converge to half. Half is the mean here. All these xi will have mean half. Right? You can get another many other. Huh? Yeah, probability. There is no other measure. Did I say measure? Right. Yeah. Measure 0 is probability 0. Probability measure. Okay. Yeah. Okay. I want to start a new topic. Is fine. Law of large number is okay. If you have any question, you ask me. Up to today, not to up to tomorrow. We will have a small class. I'm having strength, so I'm talking. I will do more tomorrow and then stop. We already missed a lot of classes. Okay. So if strong law of large number is okay, I will want to define something new, which is something important. This is what is called conditional expectation. We have already seen conditional probability. This is just an extension of that conditional. Okay. So this is the expectation of one random variable with respect to another random variable. Okay. Of course, if they are independent, then there is no condition with them. This is just a generalization of conditional probability. You will check it when so whenever we want to talk about conditional probability, we just have to take indicator function, replace a random variable with indicator function, then we'll get something about random. You'll see what it means. Okay. So x, y are two random variables. One will depend on the other. They are not independent. If they are independent, there is no conditioning between them. Okay, two random variables. Okay. Then yeah, we'll come to that. But conditional expectation is not a number, it's a random variable. Come to that. I will give you another definition also. The usual definition I am giving. Okay. Then I will. So we are assuming discrete random variable, okay, for the time being. Conditional, we will define it in a different way. Both we can club together through a different definition, which I will say, but we will not use that definition, okay, which I will generally remark. Okay. X, Y are two discrete random variables. Okay. Then, so we can talk. The conditional distribution is this. Okay. So of course we know what is f of x. F of x equal to probability of x less than or equal to f xx. This probability of less than x, right? Okay. Then f maybe y I put. Okay. Fy given x at x is nothing but probability of y given x given this set x equal to x. Maybe y here. I'm sorry. Sorry. This is just conditional probability. Probability of this set given that set. This is a set. All those omega such that x equal to x. All those omega such that y is less than x. This thing makes sense. These are all just set. Should I write it as set? This is okay, no? Huh? Right, yes, okay. This is, I'm just saying, probably this is just equal to probability of all omega such that, okay, I mean, it's okay, okay. So to make it very clear, let me do this. So since you wanted it, later I will use it. What is this f of x? F of x is the probability of this set. Okay, what is this set? Maybe I put a bracket before that. Okay, this set, all those omega such that x, so I put x here. Okay, x of omega is less than or equal to x. Okay? This makes sense. All those omega such that this happens. Okay, now probability of y, I mean, I wanted to use y, okay, given x of y equal to probability of, okay, probability of, this is a conditional probability. Conditional probability A given B, you know the definition. Okay, so A is this. A is all those omega such that y of omega is less than or equal to y. This is a set. Okay, given all those set x of omega equal to x. This is another set. Okay, number x is a real number. X is a real number, y is a real number. And this will make sense. I mean, we define the distribution, no? Distribution is x, distribution of f of x is probability of this set. This merge. No, this is the definition for x. If you want, I put, if you don't want any confusion, I put this, right? Okay, y of this less than y. Okay, this is another x omega equal to x. This is just number here. Okay, okay, this is what you want. Now it makes sense. Now it makes sense. F y given x such that y by x. This is just a notation. Okay. You wanted what is this x you are asking? Okay, this is okay. This is okay. So instead of omega, I just write y less than or equal to omega y. That's okay, no? That is okay. So similarly, if fx is the what is confusing? This is the distribution, conditional distribution of y given x at y by x. This is just a notation. If I write like this, that's giant distribution. No? So I write it like this. It's just a notation. This is just y comma x. This is just y, just a notation. There is no division or something, just notation. You write like this if you want. Okay. Okay. I don't want y comma x. That will be y comma x means giant distribution. That's a notation for giant distribution. So I don't want to write it. Okay. So similarly, here also I will do the same thing. Fy, you know what is Fy at y? I'm just writing it same thing. Probability of this set. Probability of y equal to y, right? For discrete random variable. We are assuming x and y are discrete random variable. Okay. So this is the definition. Now I want to write Fy given x of y. You want this? Okay. I may forget. This is it. I mean, I may tend to put this. So that's why I was using it. Okay. This is equal to just the definition, probability of y equal to y. Okay, this is said given x equal to x. Correct? This is the definition. This is the conditional density, conditional mass function. Okay, conditional mass function. This is conditional distribution. This is what is called. We will not use this. That is used for continuous. Continuous probability. Continuous probability. We don't have then this mass function. We have to use the distribution. So that is for that purpose I defined that. You can just forget it now. Just the definition which we will use later. So for the time being, we use mass function. So given a random variable y, we have a mass function. Okay, given a x, we have another mass function. This is the conditional mass function. So what is this? This is what is called conditional mass function of y given x. Okay, but this is actually equal to this thing is equal to, by definition of the conditional probability, x y of x and y. This is division, okay, divisible, divided by f x and x. Just think about it. This means probability of x equal to x, y equal to y. Capital X equal to capital small x, capital Y equal to small y. This is just the definition of conditional probability. That is the intersection. That is what precisely this joint density. This is the joint mass function. Okay? And this is just the mass function. This is by definition. So this is just direct. There is nothing. This is just to remember. You should remember this. Okay, that's all. Okay. Now we have got something. Now the conditional expectation we want to define. For that, we define a function chi of y given x at, let's say, let me write one more thing just to make things more easy. Conditional expectation of y, just to make things clear, I'm writing these things again and again. Expectation of y given x equal to x. That means you just take the see, given a random variable y, you have a mass density function, which is given by this. Given y and x, you have a density function. This is also a density function. Okay, but this is given by a conditional density function. Okay, if you sum it, it will be you check, sit and check. It will be this will be density function, means the sum should be 1, which will be the case. Okay, so you have a conditional expectation. You have a conditional density function. You take expectation with respect to the conditional density function. Okay, this is conditional expectation of y. This is a number. This is not conditional expectation of y given x equal to x. This is not given x, y given x. That I will define again. These two are different. Okay, conditional expectation of y given x equal to x. This is equal to summation y in R. Of course, the sum is countable sum only. Y times f y given x. This is y given x f of y comma x. Okay, sorry. Okay, this is okay. That's all. Is okay. This is okay, no? I'm just taking the expectation. I'm just summing. Okay, there is no confusion about this. So here comes the main picture. Okay. Now you have this function y given x of x. This is, I'm defining a function at x is equal to that function. Okay, that is just the conditional expectation of y given x equal to x. Okay. Now define E of conditional expectation of y. This is a y given x equal to the function of x. This is the function of x, right? X in R. This is a function from R to R. Chi is a, where should I write? Chi is a function from R to R. Okay. X is a function from omega to R. You can compose those two functions. Function of a random variable we define, and this is equal to this. This is the conditional expectation. Okay. This is conditional expectation of y given the random variable x, not x equal to x, given random variable x. This is how it is defined. Okay. Notice E of y given x is a random variable. Okay. X is a random variable, chi of x is another random variable. Chi is a function. Okay. For each omega, this takes a value. This is a function. This is not a number. Expectation is usually its domain is omega. X has domain omega, chi of x has domain omega. Chi is this function. Okay. It has omega. What happens is this conditional expectation, initially you had a random variable y. This conditional expectation is a function of x. That's what it means. Okay. If you want, this is if you really want to know what happens is the following. You have all random variables. Okay. All random variables. And your y is some random variable here. And x is another random variable here. Now you take all those f of x. F is some f of x. F is some function. I mean, since it is discrete, we are allowed to have any function. Otherwise, we need to have restriction. Okay, we cannot have all function. Okay, so you take any function R and you fix a random variable x. X is another random variable x. Okay, then you take all functions of x. That forms a space, vector space. If you have f is there, minus f is there, f plus g is there. So it's a vector space. This is a vector space contained in this. Now y is something which will not be here. Now you're kind of projecting it onto this. If you want no projection, it is some sort of projecting onto this. Some projection. Not no orthogonal projection. This is not this conditional expectation under some condition will be unique. This is actually a projection. You need not know. What you got is instead of y, you got a function of x now. Right? This is a function of x. So this is conditional expectation. Okay? Initially, you had something and you got a function of x. Okay.
So conditional expectation is a projection.
Conditional, like the E is a projection. E is the projection. E. You do E of y. This is, you put a point here.
E of y given x?
Y going to E of y given x. This is the function. This is a projection. Okay. You put point. Y going to this is a projection onto that. Okay. Projections means if you apply it second time, it should be the same. It's idempotent. Okay. Here. I mean, when you have inner product, there is more condition. Okay. Here it's only idempotent. That's what I mean. Okay, so that we will come to the definition later, but this is our definition. We use this definition to define conditional expectation. Okay, most important property of the conditional expectation is proposition. Okay, you have expectation E. This is a random variable. E of y given x is a random variable. So you can take the expectation. This is the usual expectation. Okay, this is same as E of y. Okay. That's all. E of random variable conditional expectation with anything. You have a random variable. E of y by x, y given x is a random variable. Okay. Now you take the expectation of that random variable, you get the original expectation. X is no more important. That number you get it. Whatever the x you take, you are going to get the same thing. Okay. This is okay. This is like projected to complex numbers. I mean, sorry, real numbers. Proof. We want to calculate this. E of this. So we have a random variable here. You want to know the mass function, and then using that, you know how to calculate the random variable. So E of this E of y by x. Okay. This is given by some function chi, right? There is a chi. Okay. So that is going to be summation x in R. Okay. That chi, this y given and all I will not write for the time being. So chi of x, then f x at x. This is the expectation, definition of expectation. Expectation is defined like that, right? Expectation, this is same as E of chi of x by definition, right? Okay. I mean, this is defined as chi of x, right? This is defined as chi of x, and E of this is E of chi of x, okay? And that is equal to this. We have already proved if you have a function of a random variable, then the expectation is this sum. We have proved this, okay? Remember, we proved this, okay? Because of that, this is true, okay? Oh no. I think it was not done. Okay. So this is the sum we have, and we want to prove. So this is what is this summation x? What is chi of x? We have defined, right? Written it somewhere. Chi of x equal to, we have that function, right? Chi of x is this, right? It's a function. Yeah, it's here. Chi of x equal to that function. So which is summation over y. This is chi of x. Chi of x here there is no random variable. It's just a function. Okay. This is y such that y f of y given x, okay, y x is right. This is the conditional expectation times f x x. I have just inserted the definition of k of x, which is this. Okay. Now summation over x, summation over y. You just write it y. Now what is this? This is f x y, x y y x or whatever, maybe y x, y x. Okay. Then fx x divided by fx. So we have only this. Now you take the interchange the summation. Summation over y, summation over x. Okay. Now you have the y here, f y x y x. If you sum it over x, you will get the mass function of x. Right? Right? This is the definition of E of y. That's all. Things get cancelled and we get. So if you take the expectation with respect to any random variable, then take the, I stop here. I will do more on conditional expectation and stop tomorrow. And we will do when the syllabus is up to this.